Imagine a world, right, where our energy needs are met simply by sunlight and water. No fossil fuels, no pollution, just abundant, clean energy flowing freely. Sounds a bit like science fiction, doesn't it? Well, today we're going on a deep dive into the fascinating world of material science. We're looking at how scientists are actually making that grand vision a tangible reality. Our mission for this deep dive is to explore some really groundbreaking advancements, specifically using a common everyday material, titanium dioxide, to split water into clean hydrogen fuel. And doing it with nothing but the sun's energy. We'll be, extracting key insights from some cutting-edge research that was sent in, showing how these tiny breakthroughs, often happening right down at the atomic level, could lead to massive shifts, real changes in how we power our lives, and frankly, secure a sustainable future.
Yeah, and what's truly fascinating here is that the core idea, using sunlight to make hydrogen from water, it isn't new at all. It actually dates back to the 1970s.
Oh, really? That long ago?
Yeah, but the constant challenge has always been efficiency, getting enough energy out. If we sort of connect this to the bigger picture, achieving practical, widespread solar to hydrogen energy requires a significant leap, a real jump in how much of the sun's energy we can actually harness and convert. We need to move beyond just proving the concept works, Get it into the real world.
Okay, right. Let's unpack this then. The absolute star of our show today is titanium dioxide, or TiO₂. You probably know it best from everyday things like sunscreen or that bright white paint on walls. But beyond those uses, it's also a celebrated material for something called photoelectrochemical water splitting. So what makes it such a great starting point for this clean energy dream? And what's its main limitation? And maybe, just quickly, what do we mean by photocatalytic activity here?
Good question. Photocatalytic activity simply means the material acts as a catalyst. It speeds up a chemical reaction, but only when light shines on it.
Ah, okay. Light activated.
Exactly. For TiO₂, it's great at using light to kickstart that water splitting process. It's a fantastic candidate because, well, it checks so many boxes. It's incredibly abundant, it's inexpensive to produce, completely non-toxic, and remarkably stable when you put it in water, and it's a big but.
Yeah.
It has one significant drawback. It's a large band gap.
Band gap. Yeah, okay.
Which means that in its natural state, it can only absorb ultraviolet light, UV light.
And UV light, if I remember correctly, as a portion of the total solar spectrum that reaches Earth, makes up only about, 5% of the sun's energy? That's tiny.
That's right, just 5%. So if you're trying to power, anything significant, a city, even just your home, with a material that only responds to UV.
It's like trying to fill a huge swimming pool with a tiny eyedropper when the sun's blazing overhead.
Precisely. You're missing out on the vast majority of the available energy.
So you need something more efficient.
Exactly. To make solar water splitting truly efficient, truly practical, and the benchmark people aim for is around 10% solar to hydrogen efficiency under standard sunlight, we absolutely need to shift TiO₂'s light absorption, get it into the visible light spectrum.
Because that's where most of the sun's energy is.
That's where about 45% of the sun's total energy lies. Much, much more to work with. So this raises a really important question for material scientists. How do you fundamentally change a material right down at its core to achieve that kind of dramatic shift in light absorption?
Okay, so the big hurdle is getting TiO₂ to see and use visible light. And scientists have tried some clever tricks, you mentioned, to modify its internal structure, narrow that band gap. What were some of those early approaches they experimented with?
Well, the initial efforts focused on what we call monodoping.
Monodoping.
Yeah, introducing just single types of foreign atoms into the TiO₂ crystal lattice. For example, adding certain metals like vanadium or chromium showed some promise. It did extend absorption into the visible light range a bit.
But there's a catch, I'm guessing.
There was. The issue that quickly came up was a significant decrease in carrier mobility and an increase in carrier recombination.
Okay, hold on. Carrier mobility and recombination. Can you break those down for us? Sounds like the energy generated was just getting lost somewhere.
You're absolutely right. Think of it like this. Sunlight hits the material, creates these electron-hole pairs. Those are the charge carriers you need to split the water. Carrier mobility is just how freely these electrons and holes can move through the material to do their job.
Okay, like traffic flow.
Kind of. And recombination is when an electron finds a hole and they basically cancel each other out before they can be used. Poof! Energy gone.
Wasted.
Exactly. So with that early monodoping, even though it could absorb a bit more light, Too much of that generated energy was just getting trapped or lost internally. It wasn't efficient enough. It turned out to be, well, a bit of a dead end for really boosting efficiency.
Right, a major roadblock then. But what about other approaches? Did they try using non-metal elements instead of metals?
They did, and that's where things got particularly interesting. This is called anion doping.
Or anti-doping? Oh,
Yeah, instead of metals, scientists started incorporating non-metal elements, things like nitrogen, carbon, or sulfur. Now, these elements, when you put them into the TiO₂ structure, they can do a couple of things. They might create new energy levels within the material, or they can sort of blend, hybridize with the existing oxygen states. Either way, the effect is that it narrows the band gap.
letting it absorb visible light.
Exactly. And crucially, it does this while keeping the overall energy levels in a good place for the water splitting reaction to still happen. Our sources specifically mention N-modified TiO₂, that's nitrogen-modified rutile nanowires. They showed their working spectrum extended quite a bit, out to about 520 nanometers, getting into the green part of the spectrum.
Okay, so anion doping was a definite step forward, wider light absorption, but the research highlights another evolution, right? Taking this doping idea even further.
Absolutely. The really innovative step, the next big idea, was something called co-incorporation.
Co-incorporation, meaning doing two things at once.
Precisely, adding both a metal cation and a non-metal anion at the same time.
Okay, why do both? What's the thinking there?
The core idea is something called charge compensation. Basically, by carefully putting both positive charges from the metal and negative charges from the non-metal into the TiO₂ lattice together, it helps to neutralize internal defects, those little imperfections that can really hinder performance.
Ah, so it cleans things up internally.
In a way, yes. It significantly reduces those pesky charge recombination centers we talked about, those points where the energy gets lost. So this strategy, it doesn't just enhance the photocatalytic activity, it actually improves the overall material quality and its ability to absorb light too. It's about creating a more, let's say, harmonious and efficient internal structure.
And what specific combination of elements showed the most promise in the research you looked at? Did it deliver a real, measurable improvement?
The combination that really stood out in the sources was nitrogen and tantalum. So NTA-TiO₂.
Nitrogen and tantalum, okay.
And yes, the research demonstrates a significant measurable boost in performance. For instance, these NTTI2 nanowires, when they had the optimal amount of tantalum, showed a photocurrent of 0.52 milliamps per square centimeter under simulated sunlight.
Okay, 0.52 ECME2. Now, just to clarify for everyone listening, that photocurrent, that's basically a direct measure of how much electrical current, how much useful energy we're generating from the light.
That's exactly it. It's a direct indicator of efficiency. How well is the material converting light into usable electrical energy for splitting water?
And how does that 0.52 compare to the previous efforts, like just the nitrogen doping?
Well, that's the striking part. It's double. The nitrogen-only TiO₂ achieved 0.26 micrometer-2.
Double. That's a huge jump.
It really is. And this isn't just a number in a lab report. Doubling the efficiency at this stage could dramatically shift the economics of producing hydrogen this way. Makes it much closer to being competitive. And this enhancement, the researchers attributed it precisely to having fewer of those recombination centers and also suppressing the formation of an undesirable sort of messy amorphous layer during processing, leading to much cleaner conversion.
Fascinating. So it's not just about the chemicals you put in, but also the quality of the material you create.
Absolutely. Material quality is critical.
Now, beyond just the chemical recipe, the physical structure, the shape of these materials seems to play a huge role too. Why are these vertically oriented nanowires so advantageous for this process?
Right. The structure is key. Nanowires or other similar one-dimensional shapes like nanorods or nanotubes, they offer several big advantages. First, just by being long and thin, they provide a very high surface area where the electrode meets the electrolyte, the water.
More space for the reaction to happen.
Exactly. More interface area. But maybe even more importantly, they significantly shorten the distance the charge carriers, especially the holes in TiO₂, have to travel to reach the surface.
Shorter commute?
You could put it that way. It means they can get to the electrolyte and do their job splitting water much more efficiently before they get a chance to recombine and waste that energy.
So it helps with that recombination problem again.
It does. This geometric advantage directly translates into much better charge separation, keeping the electrons and holes apart, and ultimately higher efficiency. It's like designing a super efficient internal highway for them.
Minimizing internal traffic jams, essentially. And the sources mentioned a specific way to make these tiny, precise nanowires.
Yes, the research highlights a specific technique called hydrothermal synthesis. It allows them to produce these ultrafine, single crystalline rutile TiO₂ nanowire arrays.
How fine are we talking?
Incredibly small. Characteristic cross-sections as tiny as about 5 nanometers. That's minuscule. And they can be grown up to maybe 4.4 micrometers long. And this exceptionally small size actually helps too. It makes it much easier to incorporate a good amount of nitrogen into the TiO₂ lattice, even at relatively low processing temperatures, so structure and composition working together.
Incredible precision. Now, combining all these insights, the doping, the structure, what happens when you introduce another element into the mix? Hydrogen. The sources mention a synergistic effect.
Ah, yes, this is truly fascinating stuff. A really significant leap, actually. What they found is when these TiO₂ nanowires are treated or annealed, first in a hydrogen atmosphere and then in ammonia, which provides the nitrogen.
So a two-step process.
Right. When they do that, the active light absorption spectrum, the range of light the material can use, extends even further than with just nitrogen. It reaches out to about 570 nanometers.
570, that's well into the yellow-orange part of the spectrum, isn't it?
It is. And this sample, the H, N-treated one, showed a visible light photocurrent of 516 macameo-2. Now, that might sound lower than the N-Terray number, but the key thing here is that this 0.16 represents a whopping 41% of the total photocurrent under simulated sunlight.
Wow, so nearly half the energy generated was coming just from visible light.
Exactly. That's a huge portion being harnessed directly from the most abundant part of the solar spectrum. A massive leap forward in utilizing visible light.
What's the secret there? What's behind this synergistic boost when you combine hydrogen and nitrogen? It sounds like it's more than just 1 + 1 = 2.
It really does seem to be. The research suggests the key is this unique chemical interaction, a sort of dance, between the nitrogen dopant and an increased number of something called Ti3+ species, which form in the bulk material after that initial hydrogen treatment.
Ti3+ PEM, and like a different version of titanium inside the material.
Sort of, yes, a different oxidation state. Without getting too deep into the quantum mechanics, the idea is that this interaction creates a more receptive internal structure within the titanium dioxide. It allows the material to capture photons, light particles from longer, more abundant wavelengths in the visible spectrum. Essentially, it fundamentally changes how the material interacts with that light, letting it convert more of it into usable energy.
It's amazing. So you've got the right chemicals, the right structure, this HN synergy. But even with all these clever modifications, there's still another crucial step in the whole water-splitting process that can slow things down, act as a bottleneck. Which part is that?
That would definitely be the water oxidation half reaction.
Oxidation, making oxygen.
Exactly. This is the part of the process that involves pulling 4 electrons and 4 protons out of 2 water molecules to form an oxygen molecule, O2. It's a complex reaction, multiple steps, multiple electrons involved, and it's typically the slowest part. The rate-limiting step in the whole photoelectrochemical water-splitting cycle. It often holds back the overall efficiency.
Okay, so if that's the bottleneck, the slow lane on the highway, what do scientists do to speed that specific part up, to unlock even more efficiency?
To accelerate that slow step, they use things called co-catalysts.
Co-catalysts, like a helper catalyst.
Pretty much. These are additional materials usually put right onto the surface of the main photocatalyst, the TiO₂ nanowire in this case. Their job is specifically to enhance the kinetics, the speed of that water oxidation reaction. Essentially, they provide an easier pathway for the reaction to happen. They lower the energy barrier needed to get it going, allowing water to be oxidized into oxygen much more readily. And they do this without being consumed themselves.
Right, like a good catalyst should. And the sources mention a particularly effective one for the N-modified TiO₂ we've been talking about.
Yes, the research points to a surprisingly simple treatment using cobalt.
Cobalt, okay.
When they applied this cobalt treatment to the N-modified TiO₂ nanowires, it dramatically improved the photoelectrochemical performance again. The photocurrent jumped by about 2.5 times.
2.5 times, that's huge.
It is. It reached an impressive 0.61 macrometer-2 overall. This really shows that even after you've done all that work improving the bulk material and its light absorption, there are still significant gains to be made by optimizing the reaction happening right at the surface.
So how does cobalt achieve such a powerful boost? What's its specific role there? It sounds like it must be doing something quite special.
The research suggests cobalt plays a really critical dual role, 2 jobs at once.
Okay.
First, it passivates surface states on the TiO₂. Now, think of surface states as tiny defects or imperfections right on the material's surface. These can act like traps for the generated holes, causing them to recombine there, wasting energy before they can oxidize water.
Ah, more traps to get rid of.
Exactly. So by passivating them, cobalt essentially smooths out these defects, which increases the lifetime of the holes, gives them more time to find a water molecule and react.
Makes sense. And the second role?
Second, and perhaps even more importantly, it acts as a genuine water oxidation co-catalyst. It directly speeds up that crucial rate-limiting chemical reaction itself right there on the surface. It makes the oxygen formation happen much faster.
So it helps the holes survive longer and makes the reaction they need to do easier.
Precisely. A very effective one-two punch.
Wow, what a journey we've really been on here. We started with titanium dioxide, basic, abundant stuff, and through truly ingenious engineering, from shaping it into these incredibly precise nanowires to carefully doping it with elements like nitrogen and tantalum, finding that amazing synergistic dance with hydrogen, and then finally adding that crucial cobalt catalyst right at the end. Scientists are really unlocking its incredible potential. They're making it possible to efficiently convert simple sunlight and water into clean, vital hydrogen fuel. Fuel for our future.
Absolutely. And these advancements, they're not just, theoretical curiosity stuck in a lab. They're genuinely pushing us closer and closer to practical, efficient solar to hydrogen production on a scale that could really transform our energy landscape. It just powerfully highlights how these targeted material modifications, sometimes changing things atom by atom, can dramatically alter performance, especially for what's arguably one of the most critical clean energy technologies we really need right now. It shows how that deep, fundamental science translates directly into tangible progress for powering our world more cleanly.
So what does this all mean for you, listening right now? Well, it means that dream, that vision of a world powered by clean, renewable energy. It's moving swiftly out of the realm of distant fantasy. It's happening in labs worldwide, and it's inching closer to mass application every day. And this isn't just about making hydrogen, is it?
Not at all.
It's about fundamentally changing how we generate energy, drastically cutting our reliance on fossil fuels, moving towards a future with cleaner air, a more stable climate. It touches everything. It's really a testament to human ingenuity, isn't it? Driven by that deep understanding of basic chemistry and physics, transforming humble, everyday materials into powerful tools for a more sustainable, less polluted future. For everyone. So as you reflect on this deep dive, here's something to maybe mull over, a provocative thought. What other common, abundant materials out there might hold similar hidden potential for clean energy? Are there other overlooked elements, maybe things we see every day, just waiting for brilliant scientists to unlock their secrets through this kind of precise engineering and innovative design? The possibilities, when you think about it, seem truly boundless. The future of energy might just lie hidden in the most unexpected places,